Hi guys, in our first video on the addition of vectors, we had looked at a concept that we can roughly describe as head to tail rule for addition of vectors, whereby said that we can have two vectors A and B being given as this, and we said that we can be able to describe these specific vectors using those symbols that I can be able to illustrate on top of those letters. So therefore, we said that if we're going to achieve our resultant vectors for the two vectors that have illustrated on the board, we can be able to achieve that one by moving either of the vectors in a parallel direction to itself, and that is going to give us what we refer to as a resultant vector, which we have described as C. So therefore, we say that we can be able to achieve C using the addition of A and B given as such, and we said that in case if we move this vector B with respect to itself, parallel with respect to itself, and therefore we can be able to achieve the same result. So this is going to be the illustration for the head to tail addition of vectors. So suppose we have this vector for A and B given as such, and we decide to move B parallel to its original position, then therefore we are going to have this vector for B at this specific point, and therefore we're going to have the resultant vector which is going to be, of course this is a vector A, so therefore we're going to have a resultant vector that is going to be illustrated as a resultant. I can just have this one as that. So therefore we're going to have this B. So the resultant vector is going to be indicated as such. So this is a new position for B. So the resultant vector C is going to be shown as such. So we said that this one can be displaying that aspect of commutative law, whereby we say that an equivalent for A plus B, which is C, can be illustrated as B plus A respectively, and therefore the addition of vectors is going to obey their commutative law as we had mentioned. So suppose we have a combination of three vectors, then therefore we are going to have a different way in which we can be able to do this specific addition of vectors. And for this specific case, then therefore we are going to expand this idea of a head to tail rule for addition of vectors and trying to describe what we refer to as the parallelogram rule for addition of vectors. Now in this case, I'm going to consider three vectors for A, B, and C, and try to see how we can be able to describe those resultant vectors from this specific case, or how we can be able to explain the law of a parallelogram in order to describe these specific vectors. So if we have vectors A and B being given as these two vectors as such, therefore we can be able to just describe this specific figure in terms of a parallelogram, whereby we're going to transfer this B, this specific direction aside, indicated for the first case for head to tail addition of vectors, and we're going to also to have that be indicated as such. So if we try to look at this, now suppose this one is parallel to this, and this one is parallel to this, this is going to describe a parallelogram from a two-dimensional figure, or a two-dimensional geometrical figure. So therefore we can be able to describe a diagonal for this given as C, which is going to be a resultant vector from this particular case. So therefore applying this parallelogram rule, therefore it's going to assist us in trying to find a diagonal which is going to be representing the resultant vector of this specific case. So that's going to be a parallelogram rule, which basically was the sum up of the first and the second case we had seen for vector addition of a head to tail rule that we have represented using example. So suppose we consider another case whereby we are having a number of vectors which perhaps cannot be represented using this parallelogram rule, and if we say that we have vector A given as that, vector B given as that, vector C given as that, and perhaps vector D given as that. So bearing in mind that this one constitutes magnitude and direction, we are going to consider a case whereby we are going to have one specific vector starting from this specific point, and we're going to perform this operation of a head to tail for vectors A, B, and then we're going to have vector C given as that, and perhaps vector D given as that. And for us to find the resultant vector, we are going to assume that this specific point, starting point, is going to form our origin, and the last point is going to be the tip of this specific vector for D that is going to be indicated as such. So for us to find the resultant vector, and therefore that is going to be an addition of all these vectors, so which is going to be illustrated as vector A plus vector B plus vector C plus vector D respectively. So this is how we can be able to achieve another alternative for trying to describe the aspect of vectors. And of course, from our previous discussion on this specific one that we have seen, these are going to be very fundamental in trying to describe vectors in a coordinate system, whereby we're going to see that the coordinate system is going to create our aspect of a point of reference, whereby we're going to describe the starting point and the end point of these vectors in terms of the coordinate or the coordinate points on that specific coordinate system. So therefore, this is going to play a great role in us trying to find the magnitude and direction as I said, especially bearing in mind that these are going to constitute various components for the two-dimensional system. Then therefore we're going to have 2 points, and for 3-dimension, then therefore we're going to describe these vectors in terms of 3 specific points as I've indicated for this one. So therefore, these are going to, of course, obey the laws of algebra addition of vectors as I've said. And we're going to, of course, see that these particular laws, I've mentioned the first one for the law of commutative law of vectors addition, which I've indicated. Suppose we have a vector which is A plus B. For addition, this is going to imply that we can be able to have B plus A being given as this, and this is going to constitute the commutative law of addition of vectors. And if we have, in case the previous aspect that we had said about multiplication by a scalar, we had said that for the commutative law, then therefore it's going to imply that if we have a scalar alpha with a vector A, this is going to be equivalent to A alpha given as such, and this is going to, of course, obey the commutative law of course, laws of algebra that we have mentioned. So the second law that we're going to look into that is going to be applicable in vectors is going to be the associative law. And now for the associative law, we are going to see that for addition of vectors whereby we have A plus B, and then this is added to C, vector C, that is going to be equivalent to, of course, A plus C plus B given as such. So therefore that's going to obey what we refer to as the associative law of addition of vectors as I've indicated on the board. And for the associative law for multiplication, if we have a vector, or rather perhaps for a scalar quantity, if we have beta that is of course being multiplied by alpha A, this is going to imply that this can be illustrated as the B alpha, beta alpha, and then this is going to be multiplied using that specific scalar. So this is going to be described as the associative law. And lastly, we're going to see the concept of the distributive law, which is going to also affect this concept of vectors, whereby if we have a scalar alpha that is being multiplied by A plus B, which are vectors, this is going to be, of course, illustrated using this distributive aspect, whereby A is going to be multiplied by alpha and B is going to be multiplied by alpha using that specific concept. And this is going also to apply the multiplication by these various scalars I've given for the first case, whereby we're going to see that alpha plus B can be described as well as this is alpha plus B can be described, or this is beta, not B. So alpha plus beta, so this is going to be given as beta. So alpha plus beta can be described as, now basically this beta was for the distributive law, so this is just correct to say that that is a vector B. So alpha plus vector B, and therefore this one can be given as into A. This one can be given as alpha A plus B A given as such. So therefore this is going to be consisting of the aspect of the laws of vector addition and subtraction, which we're going to see being exploited later in our application. So catch us in our next video where we're going to look at the different aspect of a vector subtraction. And this is of course going to form generally not our last, but some of the concepts which we are going to of course see in this aspect of vector algebra, especially now that we have done on the first two for addition and parallelogram addition and of course the head to tail addition. The last one is going to complement on what we have said, of course, and these are going to assist us in trying to tackle various areas that we come across, especially in mechanics. So that is it for now, guys. Bye, God bless you.